Hello, I'm Xiao from INRIA, France. I'd like to present our work on the non-emission and repairing of NURBS models. This is a joint work with Geometry Factory. I'd like to introduce first what we aim to mesh and repair with our method. In nowadays CAD systems, NURBS models are dominant boundary representations, which we call BREP. In a BREP, the boundary curve of each surface has three representations, including one 3D intersection curve and two trimming curves in respective parameter spaces. In general, these three different representations do not match each other in 3D space, which leads to trimming defects such as gaps, overlaps, intersections, and end mismatches between trimmed surfaces. So a NURBS measure has to deal with these defects to generate a valid surface or volume mesh. The prevalent NURBS measure today, which we call parameterization-based NURBS measures, generate surface meshes by discretizing surfaces individually and afterwards deal with the mesh connectivity between neighboring surfaces. The major downside of this method is that the mesh will be dependent on the NURBS layout, and the remeshing may be required to get a better mesh quality. This is a brief list of related mesh generation and repair methods. For the parameterization-based method, we can use mesh quilting method to match surface boundaries, or virtual topology to merge the topology of adjacent surfaces to reduce the dependence on NURBS layout. If the resulting mesh still contains defects, we can apply either local topology and geometry repair or global remeshing to get a watertight mesh. Alternatively, we can use Delaunay meshing using protecting balls to cover all the surface boundaries such that the regions inside balls are completely protected and are not queried in the meshing process. We have two objectives of our NURBS measure. One is to get a valid mesh with different types of trimming defects repaired with a unified scheme. And the other one is the parameterization-free meshing to be independent of NURBS layout, in which we adopt the Delaunay meshing. As we know, the Delaunay meshing involves a number of intersections between the Delaunay dual edges and the surfaces in the filtering and refinement process. So it's crucial to have a robust intersection oracle. Trimming defects in the NURBS model pose a challenge to the intersection computation. For example, an intersection point will be missed if a dual edge passes through the gap, or there will be duplicate intersection points if the edge intersects overlapping regions. All these cases of wrong intersections will affect the Delaunay refinement and filtering. So we want to solve this issue while being independent of NURBS layout. This is an overview of our algorithm. We first cover all the surface boundaries with balls. The ball sizes are adaptive to the surrounding geometric features. Sharp features and smooth surface connections are treated differently. So we actually divide the whole model into three subdomains. Sharp features are covered with protecting balls, so they will be preserved in the final mesh. Smooth surface connections will be covered with blending balls. Inside blending balls, the original surface is replaced with implicit surface. In the defect-free region, the intersection is computed with NURBS surfaces. Inside blending balls, however, the intersection is computed with implicit surfaces. First of all, let's take a look at the ball covering process. We need to consider the ball covering along a boundary curve. We work along a 3D intersection curve, and the two end balls are determined first considering geometric features. We will introduce how to determine the ball size later. The working steps are guided by auxiliary balls. The size of the auxiliary ball is 1/3 of its preceding ball. The working continues until it reaches the end. And there are two scenarios approaching the end. One is that the auxiliary ball intersects the end ball, and we simply enlarge the auxiliary ball. The other case is that the last ball already intersects the end ball, and we also enlarge this ball size to ensure the sufficient overlapping of adjacent balls. To determine the ball size, we consider several geometric features. The first is the surface separation distance, which is to ensure that balls on two different curves do not intersect. We compute the closest distance between the ball center and the surfaces that are not adjacent to the curve, and we take 1/3 of this distance for the ball size. The second is the curve separation distance, which is to ensure that non-adjacent balls on the same curve do not intersect. The strategy of computing this distance is to grow the ball gradually until it intersects a non-adjacent curve segment. We also take 1/3 of this distance for the ball size. In addition, we consider the local curvature at the ball center such that the ball size is reasonable where the curve has a high curvature. The third measure is to ensure the prescribed sharp feature approximation error. Sharp features are preserved in the final mesh by connecting the centers of protecting balls. So the protecting ball size is constrained by the edge approximation error. We also use the ball growing method to estimate the ball size. At each growing step, we can get a chord connecting the ball center and the intersection point with the curve, and we measure the distance, the deviation between this chord and the curve. The ball grows until this deviation reaches the prescribed error. The last factor is the defect size to ensure that trimming defects are completely covered by balls. The ball size is then determined by all these features, and we also check the sufficient overlapping between adjacent balls as the final step. After generating balls, we approximate the NURBS surfaces inside blending balls with implicit surfaces. We use the Delaunay interpolating splines, which interpolate the surface points and their normals. Here we give two simple examples to illustrate the interpolating splines. We can use a few interpolating points and their normals to get a satisfactory approximation of the original surface. And we use this interpolating spline to construct an implicit surface inside each blending ball. We select sampling points on the surface in the following 4 regions: the ball boundary, the intersection of adjacent balls, truncated cone inside the ball, and points on the 3D intersection curve. So a handful of sampling points from these regions can give a tight approximation of the original surface inside the blending ball. But since the implicit surface is constructed for individual balls, they are not supposed to be continuous across the adjacent balls. So we have to blend the implicit surfaces between adjacent balls so that the implicit surface is continuous and the intersection computation inside blending balls is consistent. So this is the blending function that we use to blend the implicit surfaces inside two adjacent balls. Next, we can design our intersection oracle. For each segment in the intersection computation, we first check if the segment intersects any ball. If not, the intersection with NURBS surfaces is triggered. Otherwise, we divide the segment into several subsegments by the balls it intersects. For each subsegment, we do either NURBS intersection or implicit intersection, depending on whether the subsegment is inside a ball. In the end, all the intersection points are collected. We now present some examples to show the features of our NURBS measure. This model has two overlapping surfaces. The overlapping region is fully covered with blending balls. The ball sizes are adaptive to the overlapping areas. In the final mesh, we can see that the overlapping defect is repaired. This model has a tapering surface penetrating between two surfaces and is non-watertight near the tip of this tapering surface. Gmesh fails to create triangles for the tapering surface using small element sizes because of the non-watertightness. In our measure, this intricate region is covered with protecting balls and repaired in the final mesh. This diamond model contains different types of trimming defects, including gaps, intersections, and mismatches. All these defects are covered with balls, either protecting balls or blending balls, depending on the sharpness of the boundary curve. As we can see, all these trimming defects are repaired in the final mesh. Another important feature of our measure is the parameterization-free meshing. For the surface boundary curves that do not represent sharp features, the mesh elements cross these boundaries, such that the mesh does not depend on the NURBS layout. We compare our Delaunay meshing with the protecting ball only method proposed by Buzayev. Instead of heuristic merging and shrinking operations to generate balls, we consider geometric features in computing the ball sizes, so we have much better control on the discretization of sharp features, as shown here in these two pictures. Also, as mentioned in the previous example, we only protect sharp features, and mesh elements will cross the smooth surface boundaries. We also compared with a Tate-Wild, which provides an alternative approach to generating a tetrahedron volume mesh if we have a NURBS tessellation. We found that for some models, Tate-Wild does not always give consistent mesh quality in similar regions with the same parameters. For example, some gap regions are repaired, but in other gap regions, tetrahedron cells are missing. Also, extra tetrahedron cells may appear in some regions where we do not expect tetrahedron cells. Our method can also be extended straightforwardly to other applications. For example, defeaturing small geometric features in a CAD model. For the geometric details, we can choose either to preserve them in the final mesh using protecting balls, or to defeature them by using blending balls. The geometric details inside blending balls will be replaced entirely by implicit surfaces, such that we can get a mesh as if the geometric details did not exist at all. We can also achieve the multi-domain meshing, where different mesh criteria can be assigned to different domains, and the mesh elements conform between domains in contact. This is an example of two turbines immersed in a spherical domain. We applied different mesh criteria to the three domains. Conclusions: we proposed a ball generation process which considers geometric features for the ball sizing, and sharp features and smooth surface connections are covered by protecting balls and blending balls respectively. Trimming defects inside blending balls are repaired by constructing implicit surfaces inside the balls using a handful of sampling points on the surface. And our method can be extended to other applications, such as defeaturing small geometric details and multi-domain meshing with different mesh criteria. So that's my presentation today about the NURBS measure that we have been developing. And we are also preparing a Seagull component for this NURBS measure. Thank you very much.